Hey guys, in today's video we're going to be taking a look at the conservation of angular momentum. So for the conservation of angular momentum, this will be pretty analogous to our linear momentum section. So let's start by recalling the form of angular momentum. So angular momentum is denoted by our L vector here, and that is just going to be equal to our radius vector crossed with our momentum. So that's to say this is for a point particle. That's to say if we have some point particle traveling in space, we can define an angular momentum about some other point in space, and it'll be the radius vector crossed with our momentum vector. So even further, we can write this as radius cross mv. So this is for some point particle, but more often than not, we're actually going to be concerned with the whole extended body. So we can also define our angular momentum for some extended body, and that will be equal to I, which is the moment of inertia, times the omega vector, so the angular velocity. So we see this right here is a little more analogous to our linear momentum, where our I is just like our mass and our omega is like our velocity. And this here is just true when we have some extended body rotating about some pivot point in space. And then this top one again is just for a point particle. So these are sort of the equations that we're going to be looking at today. And then the only other thing we need to take note of is that similar to our linear momentum section, angular momentum is only conserved when there are no net external torques acting on our system. So we have to get a system which is isolated, which means there's no external torque. And so the only way, and the way we can sort of decide that, is we can recall a torque is just going to be our radius vector crossed with a force. So we have some system and we want to decide whether angular momentum is conserved. We can look at all of the forces acting on the system, and if any of those forces give us some net external torque, the angular momentum will not be conserved. Otherwise, we can use this conservation of angular momentum, and then that will just amount, recall, to Li is equal to L final. So just whatever angular momentum we start with will be the same as what we end with. Okay, so let's go ahead and look at today's problem statement. A 500-gram bird is flying horizontally at 2.25 meters per second when it suddenly flies into a stationary vertical bar, hitting it 25 centimeters below the top. The bar is uniform, 0.75 meters long, has a mass of 1.5 kilograms, and is hinged at its base. The collision stuns the bird so that it drops straight down to the ground. What is the angular velocity of the bar, A, just after it is hit by the bird, and B, just as it reaches the ground? At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out over here. So we have a bird flying towards the bar, and then after the collision, the bar will rotate towards the ground. So we're asked to solve for the initial angular velocity right after the collision, and then also the angular velocity as the bar reaches the ground. And I've just defined this r vector, which is going to be saying we want to take this hinge as our pivot point. So these are also some distances we'll be needing. So our first thought, of course, is we have a collision, so we should think of momentum conservation. But we also see we have rotational motion because this hinge is going to force the bar into a natural rotation. So therefore, linear momentum conservation is not going to work, but really we want to be using our angular momentum conservation here because we have some rotational dynamics. So what we want to look at is we want to say when is the angular momentum conserved, and then we want to use that to solve for what we can solve for. So in this case, our first step will be to split up this motion into two motions. So one will be this sort of initial scenario. We're also, let me do this in green. We're also going to have a final scenario after this collision where, I'm going to exaggerate this a little bit, but where the bar is rotating downwards and the bird is just falling down to the ground. So this is initial, and this is sort of a final dynamics. So our first stage of motion will just be the collision itself. So we'll assume this collision is very quick and forceful, and so as this collision occurs, we see that our angular momentum should be conserved, much like linear collisions. Because there are no net external forces, we see this as an isolated system during the instant of the collision. So what we want to solve for first, for part A, is just the angular velocity right after the collision. So that's great. We can really just go ahead and use our angular momentum conservation for this stage, which is to say our initial angular momentum should be equal to our final angular momentum. So here we see initially we have a particle moving with respect to some pivot point, and then finally we have some extended object moving. So these two are going to be of slightly different forms. Our initial angular momentum will be equal to r crossed with mv, and our final angular momentum will be equal to I omega. So this is sort of from the beginning we were called, we have two different forms, whether it's a particle or an extended object. And so this is going to be our conservation law. So now all we really need to do, we want to solve for this. I'm going to call this omega initial because it's the initial omega of the bar. So all we want to do here is solve for our initial omega. So we really need to look at this cross product, and that's really the tricky point here. So to do that, we see we have our radius vector r is just defined from this pivot point to the bird. And so this cross product seems a little bit complicated because we have some angle here which will be changing as this bird gets closer to the bar. But if we recall cross products, this cross product is also a little bit more simply written as r perpendicular times mv, which is to say we can take the perpendicular component of our radius and just multiply it by the momentum. And so when we do that, we see that the r perpendicular, which is defined right here, our r perpendicular component is the same at all times of this bird's motion before it hits the bar. And therefore, this right here we can solve for right away. We know our r perpendicular will be 0.5, looking at these distances here. And we know our mass and our velocity. And this should be the mass of the bird, so let's go ahead and be a little bit careful here. That should be mass bird. So this will be equal to I times omega initial. And our velocity is a vector, and so is our omega. So you can follow along in your solutions at home, but you should be able to solve this directly for our initial omega, which is the omega the instant after the collision. And that should give you 2 radians per second. And of course, recall that this is a vector. And so therefore, the direction of this vector we have to get by the right-hand rule. So you can see here the bar should be rotating this way. So our thumb points out of the board. So this is really the direction will be, into the board. So the direction will be into the board. Okay, so this is for our first part of our motion. And so this is for part A. We have our initial angular velocity. So now we want to look at this second half of the motion when the bar is falling down. So as the bar is falling down, we see that we have some force we didn't have to worry about before, which is the force of gravity pulling down. So at this point now, we have this gravitational force, and we can see this is actually going to exert a torque on the bar. And so the reason is we have our r vector here is going to be along the bar. And so our force of gravity will have some perpendicular component to our r vector, and therefore we are going to have some non-zero torque. If r and force were parallel, we don't have to worry about them. But once they are perpendicular, or some component of them is perpendicular, we have a non-zero torque. And therefore, we see this gravitational force is going to work to sort of speed up the rotation of this bar. So we cannot use angular momentum conservation anymore because we have this torque. So what we have to do, in fact I'll do this in green, is use another conservation law. And so in this case we see while angular momentum is not conserved, our energy should be conserved at this point. And the reason is the only force that we're worried about is the force of gravity. And we know that gravity is a conservative force. And so therefore the energy here should be conserved. And so the only tricky point, which you want to think about, is of course we have a hinge down here, that's this point, which is going to in general put some force on the bar. And so we could be concerned that that might be some non-conservative force and that might be troublesome. But really in this case we see the hinge is only going to work to keep this bar rotating. And the hinge is never going to work to speed up or slow down the center of mass of the bar. That's not what this hinge is here for. It's just here to keep the rotation occurring. And so therefore, if the hinge doesn't work to speed up or slow down the system, it's not going to do any work on the system, and therefore it is not going to change the mechanical energy at all. So therefore, our energy will still be conserved. The only force that's really going to be operating here and that's going to concern us is our gravitational force. So what we can say, of course, is our mechanical energy is conserved. So E initial is equal to E final for the second scenario of the bar rotating towards the ground. So our E initial here, if we think about it, it starts with some gravitational potential. So as usual, that will be mgh. In this case, of course, this has to be h center of mass, which is to say we have an extended object, so we need to treat it as if it were a particle at its center of mass. And so we have this as our form for the gravitational potential. We will, of course, set the ground to be zero potential. And so other than that, it also has some rotational kinetic energy from its initial rotation. So we can write that down of the form 1/2 I omega initial squared. And this m here, we should also be careful, is going to be m of the bar. So I will call that m prime, which is to say the mass of the bar, which is not equal to the mass of the bird over here. And so similarly in our I, and also in our I up here, we had to be taking into account the mass of the bar, not the bird. So you should be very careful when you go through the solutions to make sure you're including the correct mass. Over here it's the mass of the bird, in this case it's the mass of the bar, here it's the mass of the bar. So we also can look at our final angular momentum. And so again, in this case, all we're worried about here is going to be the bar, so all of these masses will be the bar. So I'll let you guys look through the solutions at home, but at this point we really have all that we need to have in order to get the final angular velocity at the ground. So if you solve for that, and of course this is a vector, so if you solve for that, you should get an answer that it is 6.58 radians per second. And again, the direction will be the same. It should be into the board still. Okay, so let's go ahead and review what we've done here. We split up our problem into the collision and the subsequent rotational motion. So for the collision, we utilize the conservation of angular momentum to find the angular velocity just after the collision. From here, we then use the conservation of energy to solve for the angular velocity as the bar reached the ground. Okay, so I hope this video helped you gain some understanding of how to utilize angular momentum for both point particles and extended objects. If you guys have any comments on this video or any of the videos here, please leave those to the comment link on the right of the video link. Thanks for watching.